Welcome to a video on BJT amplifier analysis. In this video we will be looking at the analysis steps, amplifier identification, amplifier parameters, so what we need to get out of the analysis, and then we will be looking at the following BJT amplifiers. So the common emitter with a bypassed emitter resistor, the split emitter, common base, and common collector or the emitter follower. We are going to do this using examples, since that is the best way to study the effects and see what's going on with each problem. It's best to tackle it using examples. Now, as I said in a previous video, if you want to design amplifier properly, you need to know how to analyze amplifier. So that way you can study the effects of each and every component. Okay, so how this part is going to work is there is a certain amount of examples for each, and I'm going to do the examples for the common emitter and then show you the simulations afterwards, then the common base and simulations when we're done with all the analysis, and same with a common collector. So I will guide you through with a first example, and from the second on you can actually pause and try it yourself. Or you can actually do that from the first one, but it is best to see what's going on and then try it yourself. Okay, so let's have a look at the steps. So the DC analysis, you're first going to remove all the capacitors from the system. Okay, all low frequency capacitors will become open circuits, all high frequency capacitors will become short circuits. Okay, so in the case of a load capacitor or a Miller capacitor, so there's not going to be any of those in these problems, but that is how you treat these capacitors. Okay, then you determine the Q point. So plain DC analysis using Kirchhoff. There is a nice video about all the biasing configurations. The Q point is important for us to find our small signal parameters. Alright, the AC analysis is best thing to do first is to identify the amplifier type. That way you know what to expect and what you are actually dealing with. Okay, so if you know the equations roughly, identifying the amplifier is the first thing to do. Okay, then all low frequency capacitors will become shorts and all high frequency capacitors will become open circuits. Okay, Q point for small signal parameters. Then you're going to switch off all DC sources. So they are going to become short circuits to ground. You're going to switch off all current sources and they're going to become open circuits. So the small signal analysis, we are removing all forms of DC. We are splitting the two analysis types. When we were doing the DC analysis, we didn't have any sources, AC sources working. Okay, then we're going to place the transistor with a model that we derived in a previous video. And then we have to determine a couple of parameters of the amplifier. So let's have a look at the amplifier types and then a closer look at the parameters that we need to get out. Okay, so looking at the amplifier, you need to check where the input is and where the output is. and it is usually named after the terminal that is common between the input and the output. So for the common emitter, the input is on the base, the output is taken on the collector, and the emitter here is the common factor between the input and the output side. Same with the PNP. The input will be on the base and the output will be on the collector, leaving the emitter common between the two. Okay, in terms of models, the model for the NPN and PNP is exactly the same. So you can treat them the same after you did your bias and everything will work out fine. Okay, so we are just going to focus on the NPN side. If we have to do PNP together with, it's just going to become longer than it's already going to be, but you treat them exactly the same. Okay, common collector, input on the base, output on the emitter. The collector is common. Same with the base, input is on the emitter, output is on the collector. The base is common between the two. Right. So, the parameters that we want to get out is the input impedance of the amplifier. So, what do we see when looking into our amp? That is ignoring the source and ignoring the load. Okay, same with the output impedance. What do we see when looking into the amplifier from its output? And we want to know what the maximum possible gain of the amplifier is. Okay, then if we know these things, we can add a load and see what happens when the amplifier is loaded. So this is the loaded gain. And what happens when we add a source resistance or the input loading together with the output. So this is the total gain, and this is typically what you will have when amplifier is functioning inside a circuit somewhere, is the total gain. So AV is the amplifier's capability, AV0. AV is with only a load. So the input impedance here is designed to be much higher than any source resistance. AV will do fine, and then GV is how our amplifier will operate in a certain setting or scenario. Right, so now we are going to jump into the examples and we are going to work through the steps explained earlier on. So the first example here is a common emitter amplifier, but let's verify. Here is the source and its input is going into the base, and the output here is coming out of the collector. That leaves our emitter common between the input and output, so this is a common emitter amplifier. Alright, next up, if we were to calculate the DC Q point, this capacitor will become an open circuit, this capacitor will become an open circuit, this capacitor will become an open circuit, and if you look in between here, you are seeing a normal voltage divider bias. Okay, so to do the Q point, just ignore everything on the input, ignore everything on the output, and a capacitor like this goes away. Right, so that is how to determine the Q point And then with a small signal, these capacitors will become short circuits. Right, so that will be a short, this will be a short, and if this capacitor is a short, that resistor will not be in the small signal model because it's in parallel with a short, and we will take the path of least resistance for the AC signal. So that resistor will not appear in the small signal. So this resistor only has a function in the DC analysis, and that is for bias stabilization. Right, and this capacitor here will become a short, making the load visible to the amplifier. Right, so the first step was capacitors. The second step was to switch off DC sources. So this will become a ground, and that will become a ground, making RB1 and RB2 in parallel with one another. And this will also make our collector resistor and our load resistor to be in parallel with one another. And then for the transistor, you can have R pi going in and then just a current source. And this terminal right here will be a ground point since all of this is shorted out. Okay, so Q point, plain voltage divider. Then we can calculate the small signal parameters from what we found. And we just discussed our small signal model. And then we can go on to the rest right here. Okay, so our source and source resistor, then the two resistors in parallel with one another. Then we replaced our transistor with the model. No emitter resistor, it's grounded. And here is our load and collector in parallel on the output. Okay, for a voltage divider bias, we determine the Thevenin voltage here at this point and a Thevenin resistance so that we can calculate the bias. So 5.47 volts, 24.8 kilo ohms, and our Q point IC would be our Thevenin minus VBE over emitter plus Thevenin over beta, and that is almost 1 milliampere. That is very close to 1 milliamp. And we can calculate our Q point, and that will turn out to be 5.7 volts. We can verify this in the simulation, but the important one to get out here is our collector current. With our collector current, we can apply our small signal parameter equation. So the Q point divided by the thermal voltage is 39.56 milliampere per volt. R pi is 5.06 kilo ohms, and R out using the early voltage of 50 volts is 50.6 kilo ohms. Just a note, if your early voltage is unknown to you, okay, just assume that R out goes towards infinite, and then this resistor will disappear from your model because then it will be an open circuit. This is a typical assumption when you're doing a design, is that R out is not part of any of your design parameters. Right. So with these small signal parameters, we can now determine the input and output impedance of our amplifier. Okay, so the input impedance is looking into the amplifier right here. So this does not include RS. The output impedance is looking into the amplifier from this point right here. So this also does not include your load resistor. And AV0 will also just contain that part of the amplifier. Right, so going to the next slide, if we are looking in right here, we see RB1 to ground, RB2 to ground, and R pi to ground. All three of these resistances is in parallel. Okay, so there is your input impedance. Looking into the amplifier from this side, we see RC to ground, we see R out to ground. So output impedance is RC parallel to R out as 4.3 kilo ohms. Right. Now, I'm not going to do this with all the amplifier types, but to find the maximum gain, you need to find V out over V in. Okay, so this here is a current source, and its equation is GM R pi. Okay, so it's voltage dependent from V pi sitting over R pi over there. So here we have a current source flowing inwards, down to ground. Okay, so the current generated here is a negative. So this will say that we have minus GM R pi, and to convert that to a voltage, we need to multiply it with the resistance that's in parallel with it. Okay, so V out is minus GM V pi times Z out. Okay, Z out is these two in parallel with one another. And then we can also note that V in is sitting right here and V pi is sitting right here, and they are in parallel with one another. So V pi is just equal to V in. We can plug it into this equation and we can find that the gain of this amplifier is minus GM Z out. So here we have a transconductance multiplied by a resistance. So this is amps per volts multiplied by volts per volts. And the currents will cancel because we are looking for volts per volts. Okay, so just plugging in the transconductance that we found here multiplied by the output impedance, we find a gain of minus 170.11 volt per volt. The negative here shows us that the output will be inverted from the input. Okay, so it's 180 degrees out of phase. And we've seen that with the small signal parameters that we should be some form of inversion because the slope was downwards. Okay, it was a negative slope. Okay, then we can convert this to the decibel scale. So just 20 log absolute of AV0 will give us 44.615 decibels. Okay, so converting it to decibels, it makes it easier to confirm your gain in the simulation software. So if you do a frequency analysis, you can then just see the log scale or the dBs and verify your gain from there on. Okay, so there is the three basic parameters that you need to determine. From here, we can find the loaded gain. So we just take the maximum gain multiplied by the output loading factor, which is the load over the load plus the output impedance. So plain voltage division, we want to see what is on the load. And we can see that there is a drop in our output. Same with adding the source. We want to see how much goes into the amplifier. So it's a voltage divider going in. So it's Z in over Z in plus our source. So this resistor right here. And we can see that our gain almost halved, and that goes to 33.27 decibels. Okay, and there is the parameters of our amplifier. Okay, so the equations that will feature in a design is typically those three, and then if you're designing with specific loads and sources in mind, these two. Okay, and obviously your gain should always be higher than any one of these parameters on this side. Right. Notes. For this emitter, common emitter amplifier, when our emitter resistor is bypassed, we will see R pi alone like this, which makes our input impedance dependent on R pi roughly, and R pi is temperature sensitive because R pi is beta over GM and GM is IC over VT. So the change in temperature, our input impedance can change, and same with our gain. If temperature dependency is not eliminated, even our gain can change over time. So this amplifier you will typically see when you switch it on. After a while, the gain will start to drop. Right. So the second example, trying to keep it a bit more fresh, I added a negative rail here to the amplifier, but our emitter resistor is still bypassed. So example 1, 2, and 3 will be the same kind of amplifier, just different biasing structures. Okay, so you can pause the video here and try and find the small signal model and all of these parameters on your own. And I will continue then in a moment. Okay. If we look at the model, our emitter disappeared again because this DC source will become a ground and this capacitor will become a short circuit, removing all of this once again. This will become a ground, this will become a short, that will become a short, and this will look exactly the same as our previous amplifier, just we have one base resistor and not two base resistors. Okay, so the small signal model will look exactly the same. The biasing is a bit different, however. So we have minus VEE, so this will become 10 volts minus 0.7. And our emitter stabilization. So again, this resistor right here is just to pin our bias point for us. And we will find that we are biased at 137 microamperes and our VCE value will be 6.16 volts. Right. VC is important because that will give us our maximum output swing together with IC RC. So that's why this is an important parameter to find. Okay, our transconductance roughly 5.5 milliamps, our pi 36.5 kilo ohms, and our output impedance of our transistor is very high, 367 68 roughly kilo ohms. As for the equations, they look very similar. Here's just one resistor now in the input impedance. Output impedance looks the same, gain looks the same. Same goes with the loaded and total gain. Just apply these voltage dividers. Okay, so I hope you got similar results. Moving on to the next example. So example 3 has a bit of a change here on the emitter. So this is the split emitter configuration that I'm talking about. So quickly pause and do the small signal model. Then I can jump between the two while explaining this here at the emitter side. So pause and then we'll continue in a moment. Right. So if we do the DC analysis, this section is going to go away, this section is going to go away, and this capacitor will disappear. Okay, so in the DC bias, we will see both of these resistors in series. So RE1 plus RE2. If RE1 is very small and you're just using RE2, it won't matter as much. Your bias will still be within a couple of percent accurate. But these two needs to be summed in calculating the DC bias. But for the AC, this will become a short, that will become a short, and this one will become a short, technically eliminating resistor RE2, leaving this point as a ground, and RE1 will remain in our small signal model. Right, so we have our voltage divider bias, and RE1 is the only difference between the previous examples and this one. So RE1 remained here. Okay, now we can calculate our voltage divider bias, so our Thevenin, and with that we get the same results as example 1. And now we just add the second resistor into our IC calculation, and this is about what, 30 microamperes less for IC Q point. So this is roughly the same as example 1. Our Q point will also differ a little bit. If I remember correctly, this was 5.7 volts. Okay, so adding a small emitter resistance here has very small effect on our DC bias. There is ways that you don't have to deal with this emitter resistance in the DC bias, and that is by placing these two in parallel with one another, and the capacitor and RE1 should then be in series with one another. So technically just a configuration with our RE2 here, and our RE1 will just sit here with our cap like that. So this is the parallel configuration, this is the series configuration. So the split emitter, we have two methods to implement it. Right, so then you can calculate the small signal parameters. These are very close to what we found in example 1. And the difference comes in when calculating the input impedance and then the gain over here. Our output impedance will remain the same. So if we look into our amplifier here, we see RB1 going to ground, RB2 going to ground, but here R pi and RE1 is in series with one another and then in parallel with these two resistors. Right, When doing the small signal model, I said it's important to replace a small x right here on the model. So anything that we see beyond this transistor will look larger because the current on this side is IB and the current on this side is IB multiplied by beta plus 1. So the same goes for any impedance on this side is for the base side it will look beta plus 1 times larger. Okay, you can prove this by doing a lot of math or just accept that if you go past this point is that it will appear larger. Okay, so we have RB1 parallel with RB2 parallel, and then I urge you to use block brackets here, and you have R pi plus beta plus 1 times RE. Okay, so first do the series comp and then do the parallel combination. Right, that will help you out a lot for not making a mistake right here. And then we get a very large input impedance of 14.6 kilo ohms. Right, so having this emitter resistor that's not bypassed, we have an increase in input impedance. So for voltage amplifiers, this is a very nice thing. Alright, it will help to reduce the losses here at the input. Okay, so GV will be much better in the end. This also opens up another avenue for us because we are dependent on R pi. But if this whole term is much greater than RB1 parallel to RB2, we can make our input impedance equal to RB1 parallel to RB2. So if this is much greater, our input impedance will be independent of R pi. That is a very good thing. Right. So remember that for designs. The output impedance we do not see in this direction, right? So right here is kind of a virtual ground for our source, right? So our current source is driving everything on this side. The other way to look at it is this resistance is so small compared to R out that we don't even bother with it. Okay, so your output impedance will mainly be RC with R out going towards infinite in any case. Okay, so RC parallel to R out remains our output impedance. Now, with our gain, there is a bit of a difference right here. And we will see here at the top that we still have our gain from our previous examples, minus GM times Z out. Okay, but this emitter resistor right here is technically a feedback resistor. Okay, it can take the voltage from the output or the current from the output and convert that information back to the input. And we know that feedback usually stabilizes gain, helps with linearizing amplifiers, and so on and so forth, increasing input impedances, decreasing output impedances. In the case of a common emitter amplifier is technically a transconductance amplifier, and we use the collector resistor to convert it to a voltage. So this emitter resistor is increasing the output impedance of the current source part and not so much helping out with the voltage amplification part of impedance there. Anywho's, so this is feedback, and feedback technically reduces the gain, so you get the opportunity to choose the gain that you want. Right, so there is books that use this as this equation of AV0 for this configuration would be RC over RE1, but that is based off the assumption that 1 plus GMRE1 is much greater than this 1, and then the GMs can cancel. Okay, so that brings about that we are not dependent on temperature anymore, and Z out over RE1 gives us the choice of our gain. But please use this equation if you don't want to make rough assumptions, because you need to test that assumption later on. Okay, but RE1 is called a degeneration resistor, so it reduces our gain. So always remember, emitter resistor extra, reduction in gain, or the opportunity to choose your gain. And we can see here that we do have a reduction in gain. Our output loading, and calculate our input loading. And you can see in this example I used a much higher input resistor, and I used the much higher load resistor. So with the output impedance here being low and the load being a high value, the loading effect is not so bad. Okay, and same with input, since we have an increased input impedance, our loading effect will not be as bad into the amplifier as well. But the input impedance and the source resistance are roughly the same values, so we can also see that our gain halved. Okay, so always remember, when a output impedance and a load are matching, this term will be equal to half. Same with the source. If they match, this will be half. That's also a nice way to determine the input and output impedance in a lab, is by knowing your way around your resistors and the loading effects. Right. Example 4. Example 4 is the parallel combination that I talked about in the beginning of example 3. And here I just applied a negative rail, and you can pause and see if you can draw the small signal model yourself. Right. Now, DC analysis shouldn't be a problem anymore. These capacitors become shorts, the voltage sources becomes grounds, this capacitor becomes a short, and RE2 is now in parallel with RE1. So in the small signal model, these two will be in parallel, but if RE2 is much greater than RE1, we will mainly just see the effect of RE1. But during the bias, since the current isn't flowing that way for biasing, only RE2 is responsible for the stabilization of the bias. Okay, so only RE2 will be seen in the Q point calculation, and this is worked out at roughly 200 microamps, 5.35 volts. And you should have noticed by now that our Q point is a half of VCC here. In our other examples where we use single rail and 15 volts, it was a third and a third. So what I said about the Q point in video 2 and what I said about the Q point in video 3, you can see that that is a very real thing with these amplifier analyses. Okay, but don't ever use the design equations when doing an analysis. Okay, it's two different things. Design equations is because we want VCE to be at 5 volts. But don't ever assume that the designer, when you're analyzing an amplifier, we're using the design rules. Okay, design rules are based upon what's good, but in a certain application, designing an amplifier a tiny bit different would have been much better. Okay, so don't make that assumption when dealing with analysis problems. Okay, transconductance, same old, same old. So 25 kilo ohms R pi, almost 8 milliamperes per volt transconductance, 250 kilo ohms output impedance of our transistor. And we can have a look at our input impedance now. So in this case, we only have one base resistor looking in, but we still have a series combination, and in the series combination there is a parallel combination. So we will take these two resistors in parallel, multiply it by beta plus 1 since it's across this point, and add R pi. And then all of this is in parallel with RB. Okay, having one resistor in this dual rail configuration makes it very easy for us to select the input impedance. I used the 5.6K bias resistor or base resistor in this problem, right? And this R pi plus beta plus 1 RE1 parallel to RE2 is an extremely large value. And as we can see with the end result, RB is the smallest resistor in this whole thing, or between the two, and Zin tends to be the value of RB. So that's what I said in the previous one of selecting your input impedance. So when this is much larger, you can select RB. Output impedance, still just these two in parallel. The gain in this one, instead of just using RE, we need to use the parallel combination of the two. And that will give us a gain of minus 70.7 volts per volts. In this problem, our load is much lower than our output impedance, so there is a significant decrease in our loaded gain. So this is about 24, this is 10. There should be a third decrease roughly. And then on the input side, our RS is approximately the same as the input that we see, so our gain should half from this point on. And there we have it. Our GV is minus 10 volts per volts. Right, so here we can clearly see the effects of our loading. So this is one of those amplifiers that we can design for a matching input impedance. very easily. Okay, although the output impedance is not matched in this case, and we have major losses because the output impedance here is much greater than the load. So typically in a design, Z in should move towards infinite, and Z out should be much smaller than R load, or should tend to be towards 0. Okay, but that is not quite possible in a common emitter amplifier. Because a common emitter amplifier is a great voltage divider, but its great downfall is that it has a very large output impedance. Okay, so not a great voltage amplifier in terms of output impedance. And that comes from the fact that we convert a transconductance amplifier to be a voltage amplifier using a resistor. Right. Last example. Later on you will see amplifiers much more with current sources, and this is also just to exercise the rule that a current source will become an open circuit. Okay, so take a moment, pause me, and see if you can figure out the small signal model of this one yourself. Right. The DC bias using a current source is quite easy. This current source sets the current that we want through this amplifier. So the emitter current here, approximately equal to our collector current, should be 200 microamps. Right. RB is just to provide a path for current to flow into our transistor here. So for AC analysis, this will be a short, this will be a short, this will become a ground, this will become a ground, but also this current source will become an open circuit. So our path is through the emitter resistor and through this capacitor, which becomes a short. So in the small signal model, we will have RE like we had it in example 3, just for one, no parallel. We have a single resistor on the bias, on the base, sorry. And using a current source makes it easier for us to choose almost any base resistor here. And RC's choice can match up with R load. So if you need to build an amplifier that has input matching and output matching, the one with a current source is almost ideal. And even with RE, you can select the gain that you want. Okay, so current source bias 200 microamperes, and this will be much closer in the simulations. You will see Q point 5.3 volts, and these values will now be a little bit more exact. You'll note that this problem is just the previous one without using a emitter resistor here. Technically, this current source has impedance if you're actually building one, but it's extremely high value. Ideal current source we assume has infinite impedance and infinite in parallel with another resistor. The value will tend to be that resistor value. Okay, so our small signal parameters very much the same as the previous problem. Okay, now this is not a parallel combination anymore. Zin tends to be closer to RB. And everything else kind of remains the same. Minus 70.7 dBs, minus 20.56, minus 10 volts per volts. This problem, except for this not being a parallel combination anymore is exactly the same as the previous problem. This was just designed to give you a bit more practice with when there is a current source in the mix. Okay, so it just becomes open circuit, nothing extremely strange. Okay, so before we do the simulations for the common emitter, here is our summary. So we have a bypass emitter resistor, so Zin is RBB, where RBB is any combination of resistors on the input side here parallel to R pi. Z out is RC parallel to R out, and AV0 is just minus GMZ out. Okay, I'm not looking at any of other equations, that is just voltage dividers at this point, nothing more. Okay, so when looking towards design, R out moving towards infinite, Z out will become RC, and the maximum gain is minus GMRC. This equation will be a bit more used when doing designs. Okay, so here our input impedance is most of the time dependent on R pi, except if we have a very small collector current, then it might be dependent on RBB. Okay, but for RBB there is two approaches when doing the bias. There is a rule of thumb, and then there is a method that we can actually design for a specific input impedance, ignoring the rule of thumb when doing DC biasing. The rule of thumb with IC over 10 is just a method of determining the bias resistors. There is more methods to do that. Okay, choosing input impedance becomes easier when using the extra emitter resistor. Note here that I use REE, so that is a combination of resistors here on the emitter. And I also use RBB, same reason as this side. And choosing an input impedance can be easier when using the extra emitter resistor. Also choosing a gain, just remember that your gain will be decreased, but this configuration is a little bit more stable with temperature changes because we have feedback. Okay, then the same if R out goes towards infinite, Z out's RC, and this equation will simplify a little bit. Okay, so let's go over to the simulations of these 5 problems, so that you can see that the results that we calculated in all of these examples are fairly close. I included the results that we got for the final gains and the biasing on the side of the simulation so that we can see how close we actually got to the calculated values and the simulated values. So let's go over to the simulations. Right, the first simulation is set up here, and I use a 10 kilohertz signal with 10 millivolts. We always want to keep V pi at about 10 millivolts, so that our output does not become distorted. So I usually start off with 10 milli here. I know we're going to have voltage division and that will change a little bit. But with the emitter resistor, ensure that the change here is not much larger than 10 millivolts. I will show you the distortions in this first simulation that happens. But when we have an unbypassed emitter resistor, you can start to increase this beyond 10 millivolts going into this amplifier because it gets divided between the V pi and the emitter. So to increase the input range of an amplifier, adding the emitter resistor is also a good thing for that. Right, but we will look at how to calculate that in a different video. Same with maximum output swing and how it relates back with linearity. This is just more about analyzing for our gains. So if we run our amplifier, let's first do a time domain, 10 millivolts in, then we have a division, and we remember that our input impedance and our source is roughly the same. So this 10 millivolts goes down to 5 millivolts going into the amplifier. Okay, so we can see that we have that input loading already, and at our output we have a very large signal, but as you can see, these two signals are 180 degrees out of phase, so that is our inverting part. Okay, so from Vs being 10 millivolts to V out, with this we have GV. So 10 milli times minus 46 should be 450 milli roughly. And here we can see that our output is roughly 450 millivolts peak from a 10 millivolt peak input. Okay, so our GV is kind of accurate in this case. Okay, but I'm going to mainly use the AC analysis to look at AV0, AV, and GV from here on forward. But we can see that we kind of have nice sinusoids going on. Okay, so if we increase this to 20 millivolts, this will be roughly 10 going in, and we can see that we still have sinusoidal waves. It's kind of distorted here at the top already a little bit. Okay, so 10 millivolts peak going into your amplifier as V pi is that edge of being not linear. Okay, 5 going in would be better, as we have at this point with only 10 millivolts here. But this is kind of the edge. If we increase this, let's make this 50 millivolts, you will see that your signal is heavily distorted. Okay, so that is due to our small signal model being for only a small portion of a curve. So there's only a small portion where it's considered to be linear, and that is the plus minus 10 millivolts around VBE. Right. So always try to keep this input small, except if there is a extra unbypassed emitter resistor, then this won't be a problem. Okay, for the AC analysis, you can use 1 volt, then you don't have to do any conversions inside the amplifier or at the baud plot, sorry. And the AC does not consider the non-linearity at all. Okay, so don't worry about that. You'll see that the gain is fairly accurate. Okay, if we quickly want to look at the biasing, if we cut this connection here, we can see that our bias is at roughly 1 milliampere. We had what 989 milliampere in our analysis. Then measuring at this point, this is not your VCE. For VCE, you need to take a measurement across the transistor. Okay, so this is node 4 and that is node 1. So if we just subtract the two from one another, this green one is now our VCE value, and that is very close to 5.7 volts, right, like we had in our analysis. Okay, so you can just check what the node values is and subtract them, or just subtract them in your head, and it will be close to 5.7. So that is the DC things that you need to measure, and it is close to what we really want. From now on, I will just do this while our signal is active. You can see that this DC offset here is close to 1 milliampere, and that the voltages is, if we take this 10 and minus 4.8, that we get our roughly 5.7 volts. Okay, so doing the AC analysis, let's just take it here at V out. We take it here in the center, we see that we have 33.3 decibels, which is the GV that we calculated. Now to take RS out of the mix, just make this 1 ohm. And now if we run the simulation, we will be seeing a V, because we have a loading effect. And that is 39 dBs, 38.8. It's very close. And to take this out of the mix, just make it something like 10 meg. Run the simulation, and we're at 44.6 dBs, which is the maximum gain, and that's also the maximum gain that we calculated. Right, and that's the analysis of our amplifier by hand and by simulation. So the values are very close together. Okay, I won't talk as much with the other 4 simulations, maybe with a split emitter again, but I will just show you that our analysis values are very close to our simulation values. Okay, let me open the next simulation. Right, here is the next one. Let's run it. And what did we had? 137 microamperes. So this offset is exactly that. And here we have 5 point, and this is node 4 again. Okay, so we can just go and say this minus that, and we are at roughly 6.1, like we calculated. This is a little bit off. We should be up there, but who's looking at the 80 millivolts that we are missing? That is not much. So yeah, our DC point. Another way to do the DC is by closing this, and then when you click on these nodes, the voltages will actually show on there. If you didn't know this, that is a nifty little trick. Okay, but we want to do the AC analysis now. So let's run this. Click here, and 20.6, close to 20.7. That is our GV value. This should be our AV0 value, 32.06. That's close to 32.3. And then lastly, our maximum gain. 44.4 roughly. And there we have it. Second amplifier checks out. Our third amplifier is the first one using the split emitter. So let's run the DC simulation here. And this one, I can't remember what the input and output was. I must have saved this incorrectly. So if we run this, we will see the maximum gain first. So 250 millivolts with a 10 millivolt input. So yeah, 24 times 10, this is roughly correct. Any case, so we have a decreased gain. Our VCE value here, that is still node 4. $5.75, close to our 5.84, and 959 microamps. This is also close. If this was 1 milliampere, it will still be fine. So this design checks out. Now just to show you the input here, let's make that 100 millivolts and run this, and you can still see that the input is kind of linear. Okay, that is due to this resistance right here, that we don't have a full amount, or the full, sorry, not full amount, the full input signal on the pi here. Okay, a portion of it is going to sit over this emitter resistor right here. So we can increase our input range by adding this emitter resistance right here, and where you can see it becomes a bit non-linear here at 200 millivolts. It would probably be more at 150 side, but in another video I will go over the calculation of. Right, on to business. Let's do our AC sweep. And our maximum gain is at 28.36 decibels. That is close to the 27.7 that we have here. And then, if I remember correct, this should be 10 kilo ohms when loaded. 26.2 decibels. So that is kind of close. And I think this was 5.6K in the original. We'll see in a moment. 22.246 and 20 decibels. So that is fairly close to the originals. And that's example number 3. Okay, so we have 5 and 4 and 5 left. Let me open those. Right, the dual rail problem. Let's run it. We had something close to 200 microamps, 198. Okay, so this is fairly accurate. DC point here. And 5.35 volts. Okay, so it should be sitting a bit up here, but that is not far off. Next up, AC analysis. Taking the output here, we have roughly 20 dBs. Okay, removing the source so that we can see the loaded gain. This is a 26.3 and this is a 26.26, so fairly close. And lastly, making our load infinite, we should see AV0 37.5, 37 decibels. Okay, so our analysis and our simulation is roughly the same. The only difference that I must think of is I selected AV for all the problems to be 50 volts. I didn't check the the VA, the early voltage of the quad 2. So if you right click this and pick transistor and you're on this page, you can look at the SPICE model, and what you want is VAF. That is the early voltage. Okay, so it should be 100, not 50. 50 is still fairly large for our problems that we're doing here, but it won't have a large effect. And the forward beta is 200. So you can get all this information from the SPICE model that's programmed here. Any case, so this design checks out. Let's go over to the last one and then we can do common base amplifiers. So here we have our current source problem. Running this, roughly close to 200 microamps. Okay, so a little bit that's not present here is what's coming from the base side, because this is technically the emitter and we're always doing this emitter and collector roughly the same kind of approach. So there is what, almost 1 microampere flowing into the base that is required. So not much of a difference. Let's quickly check this out. And 5.3, close to 5.3. AC analysis. $20 dBs for GV, 26.24 dBs for AV. So this is closer than the previous problem. And lastly, our AV0, 37.5. This we calculate 37, but even in the previous simulation we got 37.5 decibels. There you have it. Let me go back to the presentation so that we can look at the different amplifier configuration. Right, so the common base configuration. This one is more used in high frequency applications. The common base typically has a very small input impedance, we will see in our analysis, but the common base has a very large bandwidth. And with high frequency systems, you're usually doing input and source matching and stuff like that. So the common base is a very good amplifier used in high frequency applications, but it still has a very large output impedance, which is not ideal, because except if it's kind of a radio receiver and you're converting at this point to something else. The problem, however, is since this input is very small, this source is gonna be limited to 10 millivolts at all times. We don't have an option of increasing the input range of this amplifier, but it has a very large voltage gain. Okay, so let's look at this for the DC analysis first, and that will be the last time that I look at the DC analysis for this amplifier type. There is only going to be 3 examples on this. There is not so many variants. The only variant is going to be the biasing structure in the end. So for DC, this capacitor is going to be open circuit, this cap is open circuit, this cap is open circuit, and what do you see? Plain voltage divider bias. Okay, now with a common base, there is a capacitor here on the biasing resistors or the base resistors, and that is to bypass both of them. Okay, so the input impedance will be mainly dependent on small emitter resistance, small Re, okay, or R pi divided by beta plus 1, because we're going to view this into the emitter of the amplifier. Okay, so you will typically see a capacitor here, which if it goes to ground or if it's bypassed and this source is switched off, these two resistors are in parallel with a short circuit. So this terminal right here of a transistor becomes a ground. Okay, then we have input and the output right there. Okay, so I'm not going to pause this one. You can pause with the next one to see if you can do it. So basically, those two biasing resistors just disappeared, and here on the output we have exactly the same configuration as the common emitter. Okay, the only interesting things at this point that I can show you is Vin is here on the emitter, right? So Vin is sitting over the emitter resistance like that, positive and negative. V pi is positive and negative over there. Okay, but this goes to ground and this goes to ground. And this point here is common. So the first thing that we can see here is that V in is equal to minus V pi. Okay. The gain of a common base will not be inverted due to this right here. Okay, but I'm getting a bit ahead. If we do a Thevenin, remember example 1 of a common emitter, this is exactly the same biasing structure that we used. So all of these ICQ and VCEQ will be the same. Our transconductance will be the same, our pi will be the same, our out will be the same. It's only the way that we're using this amplifier that differs. We're using it as a common base, so we didn't do amplifier identification. Input on the emitter, output on the base, output on the collector, and the base is common between the two. So this is a common base by the definitions laid out earlier. Okay, so many people are afraid of a common base because this right here looks very complicated. It's not as complicated as it seems. If you remember the rule that I said to put an X right there, this will be fine. The input impedance is when we're looking into the V-in terminal. Okay, so we are seeing this resistor, we are seeing this resistor, and since both of them are going to ground, they are in parallel. Okay, but we are seeing R pi beyond this cross that we draw. So this is just R pi divided by beta plus 1. Or, per definition, small re. Sorry, it's difficult to write with the mouse. Okay, so it's re parallel with re, or if you calculate it, R pi just divided by beta plus 1. And these two are in parallel. That gives you input impedance of 25 ohms. Right, so re is a fairly large value. R pi is a fairly large value, but it's dependent on beta. Okay, and the transconductance. So this input here is extremely sensitive to temperature changes. So with these high frequency amplifiers, if it uses common base, will typically have cooling to keep the temperature in check because we don't have any form to stabilize the temperature right here like the previous problems. Okay, but you see we have a very low input impedance, so for matching with low impedances from sources, this is a very good amplifier. Excuse me. Okay, so Z out remains the same, RC parallel to R out, that being our virtual ground. And by applying the previous equation with transconductance and knowing that V pi is minus V in, this became a positive. So AV0, 170.1 volt per volt, and you will recall that this is very close to the values that we had in example 1 of a common emitter. So it's exactly the same. For the gain, it's just not inverted. Output impedance is the same. Input impedance is very low. Right. So, loaded gain. This is a very large load connected here, so not very high losses for AV. And GV we have, this is 50 ohms, and the input we are seeing is 25 ohms. So we will have a very large loss right here. Typically 2/3 will fall away, and 49.6 volts per volts. Right, and that is our first common base example. The common base is also very easy to design because the biasing resistors doesn't interfere anywhere with our parameters. This emitter resistance, which is part of a bias, can interfere a little bit if it's a too low value, but in the end of the day, this value is extremely high, so the input impedance will tend to be R pi over beta plus 1, or approximately 1 over the transconductance. So if you have a very high current, bias current, the impedance will be very low. So you need to decrease the collector current to actually match this with something. So input impedance is very dependent on the collector current and the choice thereof. The best option for these amplifiers is to actually have a current source to stabilize it. But in any case, moving on, pause and try to do example 2. The only difference here is the biasing and having dual rail. Right. So if that goes to ground, RB disappears. This is ground again. Output's the same, input's the same. This becomes a ground, that becomes a ground. And look, our small signal model is the same as the previous example. Okay, biasing structure, the same as our example 2 and 4 of the common emitter case. So 198 microamperes, 5.35 volts, same small signal parameters. And when looking at our equations, nothing has changed, but we had a much lower collector current, so our input impedance kind of increased. Okay, so here decreasing collector current is very good for our input impedance, and you can also see that it is very dependent on our input on our collector current right here. And in this case we have a gain of 193 with a very large RC that we're having. Loading, our output impedance and our load resistor are technically very close to one another, so this is roughly a half. And the input, we have 50 here and 125, so the loading effects for this example won't be as harsh as example 1, and we end up with 97.5 volts per volts gain. Okay, last example of common base. Here we only used a current source. Anyways, pause the video and see if you can find the small signal model and go. Okay, so this current source will disappear. This will become a ground, but it doesn't matter. That will become a ground. This resistor will disappear due to this capacitor. And other than that, everything in this problem will remain the same. Okay, now there is no emitter resistor present in this problem because the emitter resistor is in inverted commas the current source, which is a very high impedance. So our input impedance becomes purely our emitter resistance of a transistor, or R pi over beta plus 1. Okay, so the current source is a very nice solution right here. Okay, our Q point, 200 microamps, 5.3 volts, and everything perfect, just like example 5 of common emitter. And let's have a look at the analysis. So Zin is now just R pi over beta plus 1, 124.4 ohms, which is closer to this 150 source resistance that we have here. Output impedance remains the same. Gain 195.2 volts per volts. The load again is close to the output impedance, so roughly half, and also roughly half for the input because 150 is close to this 124. And there we have it, and that is the common base example. So this current source only biases and then disappears from this entirely. Okay, so looking at the summary, the input impedance is REE. In the case where our emitter resistor becomes very large, our input impedance becomes roughly RE, which is 1 over GM. So this makes designing really easy. Output impedance matching, R out moving towards infinite, Z out will just become RC. And the gain is GM RC in the case where R out becomes infinite. So the design of a common base amplifier is extremely easy. It's only based off these couple of equations. And in general, you try and select REE, which is a biasing part of a circuit, to be much higher than RE. And typically anything you get here will be much greater than 1 over GM. And it will not have a large influence. Okay, so let's have a look at the simulations. Okay, so with this first one, we can check the bias. We started with the AC simulation, sorry. We can check the bias just to show you that adding the extra components or changing the amplifier type had really no difference in our bias. Okay, so still at roughly 5.7 and this is still roughly at 1 milliampere. So this was the same as the first common emitter problem that we had. So we don't have to look at the bias anymore. We know that the bias analysis is kind of accurate. So just gonna look at the AC here. And see if that lines up. So first, our input is halved, and we want to look at the output. So for GV is 34.45 decibels. Here we have 33.9 in this problem. Okay. Let's make RS very small so that we can see our GV. Thirty-three point 33.46, and let's make our output very high so that we can see our maximum gain, 44.6 decibels. So this amplifier checks out. Okay, on to the next one. Alright, next one was with a 200 microampere bias, just like the current source one would be. If we run the simulation, we have our GV up first. 58 dBs. Great. Make that 1 milli. Let's run this. Goes up to 40.8, 40.9 dBs. So our AV checks out. And lastly, our AV0 at 45.8. And this is 45.7 dBs. Okay, so again, the calculated and simulated values are very close to one another, and this amplifier does check out. And let's see how close this is to 0 minus dB range. Actually funny. Okay, that's it for the common base simulations. Let's look at the common collector. I forgot about the current source problem. Anyways, running this 200 microamps more accurately than the previous method. Let's go to the AC model, run this, and our gain here for GV is 34.3, 34.1 that we calculated. Let's look at our AV, 40.9. Here I have a mistake, 41.6. That is fairly close. And the last one, AV0, 195 volts per volts. Make this large. And 45.9 roughly. So yeah, now we can go over to the common collector problems. Right, our common collector examples. So there's a couple of things that we need to go over before we jump into this example. And the common collector is to drive small loads. Okay, so it takes the input and it will duplicate the input at the output side exactly. And this is due to the fact that its input is on the base and its output is on the emitter. For DC, we have VBE sitting here. But if we are only viewing AC, the DC disappears. So these 2 points will be exactly the same. So the input and the output is the same. So AV0 should be equal to 1 for a common collector amplifier. Okay, so the purpose of common collector amplifier is to supply current to a smaller load. So this is a driver circuit or output stage of some sort. You'll also notice that I use the different biasing, and I use the base bias here. And the thing is, the current used in one of these common collectors are very high. So there is a high current requirement from the bias here at the back, and that decreases the resistors on the input side. And we know that a base bias has a very large resistor value, and you can see that in this problem it's already a very small value. So the bias can decrease your input impedance by quite a lot. So that's why I went to a biasing base bias scheme, and we have emitter resistor for stabilization. Looking at designs, you will typically try to design these two voltages to be exactly the same, so that we can achieve maximum swing, since the purpose of this is to be a voltage follower. Okay, so it uses very large amplitudes. So V pi is not a determining factor here anymore. We are looking at these 2 points. V pi is not featuring at all. So yeah, let's do the DC analysis. So the DC analysis, you just cut away those two, and it's a plain base bias like that. And for AC, these two get connected, so there is no bypasses for the common collector. It's mainly an input and output capacitor. Okay, so analyzing the bias, we get 84.5 milliamperes and a Q point of 3.1 volts. So that Q point is not really acceptable since we have 10 volts to play with. This should be more or less around 5. But this is an analysis, not a design, and that is what our Q is. Okay, very high current, because this is to drive a very small load, and in turn we will have a very large transconductance. R pi will be small, and Re will be R pi divided by beta plus 1, which is in the milliohm range. We do not calculate R out here. It is not really featuring in our analysis at all. If you really want, R out is extremely high and will be in parallel with Re and R load. But if this is 100 kilo ohms, it's already much greater than all of these, and it does not feature in our equations. Okay, so the input and output impedance. For the input impedance, we are going to include the effect of our load resistor. Okay, we already know that AV0 is 1 volt per volt or 0 decibels. Okay, so our input impedance gets calculated including our load resistor. Since we will only be determining AV and GV. And first we can see that our input impedance is already a very low value. It's 3.7 kilo ohms. So R pi in here is almost neglectable, and our input impedance is purely on beta plus 1 Re parallel to R load. We include the load here because these two values are very close to one another, and it will influence it will influence our input impedance quite largely. Okay, if we're just using Re, this will be a very higher value and will make it inaccurate for our GV calculation. Okay, Z out is when we're looking in from our load over here, and we see our Re in parallel with R pi plus RB, and that is when we have no source connected, and we are seeing everything through the transistor from that point on forward. So we have RB plus R pi over beta plus 1 in parallel with Re, and that gives us 21 ohms. Okay, so the output impedance of a common collector amplifier should be a very low value. Okay, determining AV. We take what we see at the load and we just do a voltage divider with RE value that we are seeing looking into our amplifier. And that is 0.994 volts per volts for this problem, which is in the millidecibel range. So there is almost no losses. This is AV0 and AV is almost equal to one another. The problem comes in when we are calculating GV. So now our input impedance and our source resistance plays a role. So now we have a very large attenuation from input to output of minus 2.13 decibels. Okay, so the issue usually with common collectors is the input impedance being too low or getting enough current to flow to be able to drive our load and biasing it with a large enough resistance. That is why they will typically use Darlington pair transistors for these output stages, is to have a very large beta value so that RB can increase in size. But in general, it's better to use a current source here and have it as a class A amplifier. Okay, the next example is dual rail. So let's go for the same analysis, and you can pause and try this one on your own. All right. If we short those, this becomes a ground, that becomes a ground, and our model will look exactly the same as the previous one. Just now that the biasing is a bit different, we have minus VEE minus VBE over RE plus RB over beta. And with this, we can actually choose our Q point exactly. And in the case of this dual rail, we want a full VCC over this transistor and the full VEE over this resistor right here, so that we can have maximum swing. So our Q point, our VCE value, we are going to calculate it a little bit differently, but this comes down to be roughly 1.46 volts. Notice that there is no emitter subtraction here, and that this is a bit larger due to the fact that we have to bias the transistor or have it switched on. So there's a bit of a drop over our emitter resistor here. Okay, so 1.4 volts. So this is minus 1.4 at this node. Anyway, calculating the transconductances again, and R pi and RE, 6.1 amps per volt. So this transconductance gives us indication that this amplifier can drive a bit better than the previous one. It has more current to supply per volt coming in. That means R pi dropped, that means RE dropped. Okay, same old as the previous problem. And we find that our input impedance here is much closer to our RB value, meaning that the impedance seen in here is much greater. Okay, so again, if the input impedance this side is much greater, we can actually determine our input impedance with our base resistance. You'll see that our output impedance dropped significantly for this problem to 4.7 ohms and applying RE over RE plus RE parallel to RL. Small drop, close to 1 volt per volt still, and the problem comes in with calculating our GV value. These two values are closer to one another, so we have 2/3 entering our amplifier, so we have a very large attenuation into our amplifier. Okay, remember this is more on current supplying these common collectors or driving small loads. So you can have a huge voltage amplifier this side and then drive whatever small load you want afterwards. Typically your BJT amplifiers will not be used alone. You will use multiples, so a common base of a common collector. If you're having a repeater circuit or a common emitter and a common collector, if you're having a high voltage amplifier with high input impedance and then have to drive some small load with like speakers or something. So amplifiers will typically be used in conjunction with one another. Anyways, moving on. Example number 3, we added a current source with 150 milliamps supply. So this is the same as the previous problem, just with a current source. So drawing the small signal model, this will disappear entirely and our load will be our only load here, and that will increase our input impedance significantly and our driving capability. So since we're driving with a current source, ICQ approximately IE 150 milliamps, and our Q point I calculated with a bit of a different equation, and I'm going to show you why. We don't necessarily know what is sitting at this node exactly in terms of DC voltages, but we can apply Kirchhoff like that to the closest ground. So we know we want VCE, we have VCC, we have VBE, we can figure out what our base current is, and we know our RB value. So the best way to calculate our VCE point is through this loop right here. So that is our Q point is VCC plus VBE plus IBRB, and that becomes 11.45 volts as our VCE value. Okay, again didn't calculate R out, and since this is the same as the previous problem, 6 amps per volts, 33.3 ohms, 166 milliohms, almost the same characteristics, just using a current source. So the nice thing about the current source is with the output impedance, the emitter resistor disappears, and we have 4.14 ohms output impedance, which is lower, just by a tiny bit, but it means that our amplifier can drive better. Our input impedance is still determined by RB in this case, but here we only used R load. So with a bit larger load, our input impedance will increase significantly. But our input impedance here is still determined by the size of our bias resistor. Okay, AV is now R load over RE plus R load. No more emitter resistor to worry about, and this is now closer to being 1 volt per volt. The problem again in this problem is we have 1K source resistor 1K input impedance, and our input is halved due to this. So if we have 10 volts here, it will be 5 volts here, but we will still see 5 volts at the output. So our problem is lying with the input impedance of our common collector amplifiers. So in summary, we're going to use R load prime in all our derivations, where R load prime is our emitter and our load together. RBB is whichever biasing scheme you're going for at the input. And you always end up with this kind of input equation here, just like what we had with the common emitter problems. Our output is very much the same as what we had with the common base problems, just we have RBB included here because it's not bypassed. Okay, AV0 is always approximately 1 volt per volt. AV is our output, or R load prime, divided by R load prime plus RE. If RE goes to infinite with a current source, R load becomes R load prime, and everything seems to simplify by a lot. Okay, and that's it for common collector. So not that difficult to analyze, also not that difficult to design. Everything is gonna turn around the output swing, and the more important part is trying to bias it and having a large enough input impedance. Okay, so let's go over to the simulations. So here is our first simulation. I'm first going to show the transient analysis. So here we have our collector current, and this is closer to 80 milliamps, where we did it in the analysis. It's 84.5 milliamps, and the DC point here, we should just go and include 10 minus this node, and it's at roughly 3.5 volts. And here we have our VCE as 3.1. Okay, in the end, the best way to get a common collector going after you've designed it is to simulate. They are sometimes a wee bit more twitchy than the values you calculated. Okay, so we started with a 4 volts peak input, and going into the amplifier, it decreases immediately. And looking at the load and what's going into the amplifier, if we're not regarding the source, is almost exactly the same value. Okay, now if we make this input much higher at 5 volts, we will start to see that the output here is starting to distort. And that is due to our VCE not being a decent value. So the output is very dependent on our VCE value. And there we start to have clipping. And this thing is supposed to be able to handle 10 volts peak to peak. Okay, so this will be 12 volts peak to peak. But if we look here, we're not close to be to 12 or to 10 yet. In any case, having this at 5, we have distortion already. Okay, so your VCE value is very important in terms of what you're trying to drive. Okay, let's look at the AC analysis. So minus 2.5 dBs for our GV, and we calculate it to be at minus 2.13 decibels. Kind of accurate. If we make our source very low, minus 114 millidecibels. Okay, so small value. And if we make this very large, let's go 10 kilo ohms, that will move closer and closer to the 0 decibel point. So the approximate of having it as 1 volt per volt is fairly accurate. So AV and AV0 is very close to one another in this problem. Let's look at example 2's simulation. Alright, example 2 had the issue of input loading here. Let's run this. We have it's on AC first. Okay, let's look at the AC first then. We have our minus 4.6 decibel drop for GV, and if we make this 1, this will become a very small value, and if we increase this, it should even decrease further. Okay, so this small change that we have here is due to the fact that we ignored our out at all times. But as we can see, our GV is fairly accurate, and these values are fairly accurate as well. Okay, so let's look at the transient. So we are inserting 10 volts peak. Then we have a huge drop on the input here to 6 volts peak, and the output is almost perfectly aligned with that. So if we were to increase this, let's go to 15. Our input is now here at between 9 volts, and we had our VCE value right there, and we have a little bit of saturation on the bottom. That is due to the VBE that we have here. Okay, so this should be in the middle. We cut this part right here, almost in the middle. So this little drop here is what's limiting our output and why it's cutting off at the bottom of the signal right here. So if we start to decrease this by a little bit, let's make this 13, we will see that the distortion starts to become a bit less. Make it 11, less. That is purely due to this VBE drop you can see that this is sitting at -8 and this is at 5, and this drop that we're having right here is what's influencing our signal. So there we have our input and our output without distortion. So we have plus minus 6 volts on the out with a 10 volt peak input. Right, so again, the limiting factor here is the input impedance and some of the DC values that is limiting our output capabilities. Okay, most of this becomes better when using a current source. So yeah, let's look at the current source solution. Right, so here we have our current source one already set up for AC, and if we run it, that is much closer to 0 decibels than any of the other problems. So our current source is helping out quite a lot. Then this was 150. Let's see what our -42 millidecibels. It's much smaller in our calculations, but this is much smaller than any of the previous problems. Not that -42 millidecibels matters. And this was, I think, 1K, or was it 560? Oh, doesn't matter. It was 1K. Looking at this values, because this is a 1K input and a 1K, and that's half the value, and it brings us to -6.2 decibels in the calculations, simulation, sorry, -6.3 dBs. Okay, so here we have our current source, and it's working quite nicely. Let's do some transient. 10 volts peak to peak input, half going into the amplifier, half being replicated perfectly. Okay, so if we go to double, our output with a current source is almost perfect. If you go and exchange this with transistors, having a built current source, you will start to have a little bit of issues um, in this circuit right here. But the outcome using a current source is usually much better, and you can also start to select the input here, and since there is a current source, it's actually giving energy, so excuse that it's cancelling. LT does not consider every scenario with a built current source. That signal will be mangled, but for a 10 actual proper 10 volt input like we have here, this circuit will function properly with a current source. Okay, so I've gone ahead and quickly replaced the current source with an actual current source with transistors, and its current is at 160 milliamps, still the 1K resistor. If we start to increase this, not enough current can get in. So it does not compensate like the real or the ideal current source for any issues that might arise. Any case, so we have a 10 volt peak to peak input, and if you look at the load, it's following it perfectly on the top, but here at the bottom this last 1.5 volts, and that's what it's moved down over the current source, is where our issue lies. So having our VCE being a bit off, we have a problem over there. So if we make this 8.5, it will work perfectly. Okay, so the input and output is the same, but due to this biasing resistor right here is why we are having issues. So making that 1K, we have a very large drop. Okay, so now we can look at alternatives. 2.2 kilo. We can increase the input impedance, but then the saturation here at the bottom might come a bit closer. Let's go just with 10K. Okay, the risk is always that not enough current is going to get into the BJT up here. So we will see the saturation soon. Let's go 15K. So as our input impedance increases, this drop that we are having kind of decreases, and our output becomes much better. So the current source solution is really the best one for common collector applications, because it allows you to play a bit more with this base resistor for input impedance, and the current source is running the current stabilization for you. So you can see how the effects play out, and here we have a almost -2 drop, and that is where our saturation will take place. When this moves down too far, it will start to flatten the bottom here. So if we make this 9, we might see that starting to happen. There we go. Starts to flatten at the bottom, and that obviously translates right through our amplifier. Okay, and that is it for common collector. And using ideal current source might not work in a simulation. It compensates for too many problems that might arise, but if you add a current source like this, you will see them cropping out, but they are not that major to deal with. But yeah, that's common collector, and thank you for watching.